Hey everyone, welcome back to Calc 2. This will be lecture 24 of the course, and in this lecture we're going to discuss the integral test and p-series. Okay, so let's jump right into it. So this, we might as well call this section 4.3, and this will be the integral test and p-series. Okay, so in this section, and really the couple following sections, we'll be exploring kind of a series of comparisons and tests for convergence, right? And so so specifically convergence of series and possibly sequences. So this will through all of this, we'll basically be looking at exploring interesting connections between, infinite series and the other calculus concepts that we've looked at. And so kind of first up here is this idea of the integral test. And so basically using integration to determine whether or not a series converges. Okay, so we'll start with the integral test and we'll talk this through. Okay, so this is referred to as the integral test. And specifically the integral test for convergence. So if f is a positive, continuous, and decreasing. So if f is, I should say, positive, continuous, and decreasing for x greater than or equal to 1, and f of n is equal to a of n, right? So this is kind of that property that we discussed in the previous section where, basically like if the terms of a sequence agree with some function f, that's what this is saying, right? So f of n is an integer, is equal to the nth term of the sequence, right? So if that's true, then the sum n equals 1 to infinity of a of n and the integral from 1 to infinity of f of x, they either both converge or both diverge. Okay, so that's the integral test. So if you're asked about the convergence of a series, it may be that there's some function you can think of which perfectly aligns with the sequence terms at the integer values. And if that's the case, and also if f is positive, continuous, and decreasing for x greater than or equal to 1, then you can integrate this, right? You can integrate that function, and if that function converges, then the series converges. And if that function diverges, that integral diverges, then the series diverges as well. Right? So either both converge or both diverge. They go together. Okay, so let's prove this one. Okay, let's try to prove this. And by proving it, we'll kind of see what's going on here pretty clearly. Okay, so this is an integral, so inevitably the integral, the proof of this thing is going to involve partition, right? So let's begin by partitioning the range 1 up to n into n minus 1 intervals, right? Equal intervals, right? Okay. Now let's draw some pictures here first. So we've got two things that can happen here. Okay, so let's say so this will be 1, 2, 3, and this will be n. Okay, let's say we got some function here, positive, decreasing for x greater than 1, and continuous. Okay, so we can draw in some rectangles, right? This is an integral right? So we can draw, rectangles that are based on the right-hand side, right? And so we know what those are going to look like. All right, so you'd have an n minus 1 here. I'll put that one in as well. Okay, and so on, right? So these obviously fill up the entire space. Right, and so this one here is going to be a2 equals f of 2. This would be a3 equals f of 3. All right, this endpoint would be a of n equals f, or a of n minus 1 equals f of n minus 1. And this is a of n equals f of n. Right, so you can kind of see how this picture looks, right? Now, similarly, you could basically kind of draw the same picture here. And so you'd have, your 1, your 2, your 3. Then over here you've got your n minus 1. Put an n minus 2 in there as well. Right, and let's imagine this is the exact same curve. It might not look exactly the same, but so then you could also consider the integral built on the left-hand endpoints, right? Right, so in this case, this is going to be a1 equals f of 1. That's a2 equals f of 2. This would be a of n minus 2, or sorry, n minus 2 equals f of n minus 2. And this one would be a of n minus 1 equals f of n minus 1, right? Okay, so you kind of see how these two are real similar, right? This one is going to undervalue the area, right? Basically because of these gaps here. This one's going to overvalue the area by those gaps. Okay. Okay, so that's kind of the picture, right? So that's what we'll be referencing this picture. This is just a basic. You've got your interval from 1 to n. Basically, like partition it equally. And come up with these these upper and lower sums, right, for the integral. Okay, so the total area of the inscribed, we'll say of the inscribed, right? That's the lower, or the upper drawing is inscribed, and the circumscribed rectangles are as follows, right? So the areas, right? So the top one is going to be I equals 2 up to n of f of I, right? So that's f of 2 plus ... plus f of n. And then the bottom one is going to be I equals 1 to n minus 1 of f of I, which would be f of 1 plus ... plus f of n minus 1. Okay. All right. The important thing here also to notice is that notice the width of these intervals is 1, right? Right. So you may be saying to yourself, how do I get an area here just by adding the value? Well, these are all of width 1, right? So the area would all, right, begin by partitioning 1 to n into n minus 1 intervals. Maybe I should say unit intervals, right? So unit width, right? So this would give you the area, or approximation for the area. Okay. Now the precise area is the integral, of course. Right. So the precise area is, hang on one second. The precise area is between these two. Well, we'll say it's the integral between these two. And how would we write it? Well, that's an inequality. It'd be I equals 2 to n of fi. That's going to be less than or equal to the integral from 1 to n of f of x dx, which is itself less than or equal to the sum I equals 1 to n minus 1 of fi. Okay, so you got kind of this inequality here. All right. Okay. So what happens next? Well then, next, so what we'd say next is that using the nth partial sum, right, and by that I just mean S of n equals f of 1 plus f of 2 plus dot 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 plus f of n, we could rewrite the previous inequality. Right, we can rewrite the previous inequality as this: S of n minus f1 equals the sum I equals 2 to n of fi, right? So this is just basically S of n would be the nth partial sum, but that's going to include the first term, which we have excluded from this this sum here. This sum was meant to represent the area using the left-hand endpoints, the right-hand endpoints, sorry. And so we still have the less than or equal to the actual integral in the middle here. So that's 1 to n of f of x dx, which is less than or equal to the other sum, I equals 1 to n minus 1, which is equal to s of n minus 1. Okay, so we just kind of added these endpoints here. All right, so we just added that part. Now, assume that the integral from 1 to infinity of f of x dx equals some value L. Right, so it follows then specifically for n greater than or equal to 1, s of n minus f of 1 is less than or equal to L, right, which implies that s of n is less than or equal to L plus f1, right? Right, so this is just kind of maneuvering things around here a bit. And therefore, right, so therefore, what happens? S of n must be what? Bounded. And it's obviously monotonic, right, by assumption. Okay, then the sum of a of n must converge. Okay, right? So if that's the case, then the sum must converge. Okay, perfect. Sorry about that. The sum must converge. Okay, so that is the very elegant integral test, right? So basically what it means is, like, look, if we're interested in whether a series converges or diverges, if it's not obvious, we can't figure it out easily by just looking at the series, we can look at the integral, assuming the sequence, assuming that the function that's equivalent to the sequence terms are, meet the criteria of the integral test, specifically positive, continuous, and decreasing, right? Okay, very good. Let's do an example. Let's see how this can be used in practice. What is the usefulness here? Well, we just kind of said what the usefulness is, but let's show it. So the question here is, does the series n equals 1 to infinity of n over n squared plus 1, does that converge? Well, let's see. So first thing to note is that f of x equal x over x squared plus 1 meets all of the criteria for the integral test. So it's positive, continuous, and decreasing for n greater than or equal to 1. Right, and so you can see that, right? So it's obviously positive. You've got when n is positive. When x is positive, I should put x here. Right, when x is positive, then this is a positive number, and obviously the denominator is positive. It's obviously continuous when x is greater than 1, right? You have an issue at x equals -1, but that's out of scope. And it's decreasing, right? Because the numerator is going to grow much faster than the denominator, and so this ratio will get smaller and smaller. Okay, so that means we can use the integral test here. So we can use the integral test. Okay, and so all we need to do then is consider, basically the integral from 1 to infinity of x over x squared plus 1 dx. Okay. And so this is an easy enough one to integrate. We can use u equals x squared plus 1, so that means we'll have to have a 1/2 times the integral from 1 to infinity of 2x dx, and then x squared plus 1. And we get 1/2 times the integral of du over u from 1 to infinity. And so 1/2 times the natural log of u from 1 to infinity. And this is going to be equal to 1/2. Now this is x squared plus 1. So the natural log of x squared plus 1, which is positive, minus, so this is 1 to infinity. We could do the whole limit thing, like put the b up there, take the limit as b goes to infinity. But you can see what's going to happen here, right? This upper piece is going to be infinite. All right, so this integral does not converge. All right, so the integral will diverge. So the integral diverges implies that the series n equals 1 to infinity of n over n squared plus 1 diverges. Okay, and so there we go. So that's the integral test in action. How about another example? What about this guy? Let's see, does n equals 1 to infinity of 1 over n squared plus 1 converge? Does that one converge? Right, so again, f of x equal 1 over x squared plus 1 meets the criteria for the integral test. Right, now you don't want to take that for granted, obviously. Like if you were going through these sections in a course, like one of the things that would be really important here would be to make sure that the series you're looking at actually meets the criteria, the theorems you're trying to apply to it. You don't want to take that for granted, right? But I mean, obviously we can, this is an example specifically about the integral test. So you do have to consider it, all right? But so this is obviously positive, it obviously is continuous, and it's decreasing for n greater than 1. Right, so you can see that's going to meet all the criteria. So what we have to do is just look at the integral from 1 to infinity of 1 over x squared plus 1 dx. Right, now this is an a squared plus u squared integral. Right, so this is going to be the arctan. But let's do this one right, since we did the last one kind of sloppy. So this would be limit as b goes to infinity of 1 to b of 1 over x squared plus 1 dx. And that's going to be the limit as b goes to infinity of arctan of x from 1 to b. And so that's the limit as b goes to infinity of arctan b minus arctan 1. Okay, and now what happens to the arctangent function as the argument goes to infinity? Well, remember the arctan kind of looks like this, right? It comes like this, and it's like that, and it's asymptotic. It's got a horizontal asymptote, which is equal to pi over 2. Right, so this is going to be pi over 2 minus, and then this one, arctan of 1, if you plug that in, you'll see that that's pi over 4. That's pi over 4. And so what you get here is a pi over 4. Right, so the integral converges, so the series will also converge. Okay, so there it is. So the series will also converge. Okay, so that's the integral test. A very, kind of simple test for convergence. Kind of intuitive also. I think the proof of the theorem is very straightforward, but powerful. I mean, a lot of sequences you can use this for a lot of different sequences. So with the rest of the time, we want to spend looking. We want to take a look at what's called the P series. Right, so kind of like the geometric series is another famous series that comes up all over the place in mathematics. And so a series of the form n equals 1 to infinity of 1 over n raised to the p power. Right, so think this is going to be 1 over 1 to the p plus 1 over 2 to the p plus dot 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 plus 1 over n to the p plus dot dot dot. Right, so that's what that one looks like. This is a series of this form is called P series. Okay. Now, when p equals 1, it's a special series. When p equals 1, this is the harmonic series, a special series in mathematics and also in music, right? So it's called the harmonic series when p is equal to 1, right? So then it's just basically 1 over n, isn't it? Yep. Okay. So what happens with the P series? Does it converge? If not, when not? So the P series, that's n equals 1 to infinity of 1 over n to the p. Two things: it converges if p is greater than 1, diverges if p is less than or equal to 1. Okay, so the series converges only when p is greater than 1. And all other times it diverges. All right. So can we prove this? I think it's useful to prove these things to see, kind of help build intuition about these series. These infinite series kind of are one of those things that even though you go through it, you learn it, you use it a lot, it's something that kind of it can remain sort of mysterious, right? So these proofs they help to kind of make them a little more transparent. Okay, so can we prove this? Well, clearly, yes, we can. So clearly, f of x equals 1 over x to the p is, positive, continuous, and decreasing, right? We can see that. Positive, continuous, and decreasing. So let's use the integral test. Okay, so the integral from 1 to infinity of 1 over x to the p dx. This is equal to the limit as b goes to infinity of 1, the integral from 1 to b of x to the negative p dx. Okay, so let's do the integration here. So limit as b goes to infinity of, now x to the negative p will produce x to the 1 minus p over 1 minus p, and that's going to be from 1 up to b. Okay, and so then the limit as b goes to infinity of 1 over 1 minus p times, b, that's a b, to the 1 minus p minus 1. Okay, so if p is greater than 1, all right, so then if p is greater than 1, what happens? Well, if p is greater than 1, then what do we have? We have the limit as b goes to infinity of 1 over 1 minus p b to the 1 minus p minus 1 will converge. And specifically because since, the term b to the 1 minus p will have a negative exponent. Right? So it'll converge, right? Because 1 over 1 minus p is not important. That's out. But so then you have the limit as b approaches infinity of basically this guy and this guy. Well, if p is greater than 1, then 1 minus p is a negative number, which means this is b raised to some negative exponent. So it's 1 over b raised to that whatever power. And so that negative exponent is going to make this thing go to 0, and you're going to be left with that part. Okay? So that's if p is greater than 1. If p is, well, so if 0 is less than p, which is less than or equal to 1, well, then the exact, basically the reverse will happen. Then, the limit as b goes to infinity of 1 over 1 minus p b to the 1 minus p minus 1 will diverge, since the term b to the 1 minus p power will have a positive exponent. All right, and that's what it's going to be all about. Okay, so that positive exponent means this will be b to some, like 1/2 or 1/3 or 1/5 or 1/8 or whatever it happens to be. So that thing is going to blow up, right? It'll grow, like just like the limit as the square root of x, limit of the square root of x as x goes to infinity will obviously be infinity. It's the same story here. All right, so this will head to infinity. That's just 1, but so the whole thing will diverge then. Okay, so those are the two cases. Okay, so just using the integral theorem, we can kind of set up this nice simple limit to interpret that's basically going to have, you're going to converge for certain values of p, and it's going to diverge for certain values of p. And so that's that. All right, very good. Let's do an example. So consider this guy, the sum n equals 1 to infinity of 1 over n. Will this diverge or converge, or what's going on here? Well, this is the p series with p equals 1. Right, so we just talked about this. We talked about how this is going to definitely diverge. Right, we could see it by using the integral test on this. So 1 to infinity of 1 over x dx. That's the limit as b goes to infinity from 1 to b of 1 over x dx, which is the limit b goes to infinity of natural log of the absolute value of x from 1 up to b. And so what do you get here? Well, you get the limit as b goes to infinity of natural log of b minus natural log of 1, and so that is infinite. Okay, so the integral diverges, so does the series. Okay, what about this one? Let's consider this guy, n equals 1 to infinity of 1 over n squared. Well, this is p series with p equal to 2. Okay, so this one, we know from the previous theorem that this is going to converge, right? But can we show using the integral test? Yes, really quickly, right? So 1 over x squared dx. And so the limit as b goes to infinity 1 to b of 1 over x squared dx. And so the limit as b goes to infinity of, this would be negative x to the negative 1 from 1 up to b. And so what do you get here? You're going to get negative 1 over b plus 1, right? Now what happens here? Well, this goes to 0 and that stays 1. So the whole thing converges. And so that means, therefore, that the series converges. Okay, and there we go. All right, so that is what we needed to talk about. So these are just the first of a handful of different different tests and properties of series that we'll discuss. So next time we'll get into some more of them. So very good. We'll end it with that. We'll see you all next time. Take care.